Good noon, everyone. My name is Tianrui Zhang from Northwestern University. Today, I'll present our paper and research on behalf of my colleague, Ang Li from California State University, Long Beach. So the title of our paper is called A Smart Caffeine Level Predicting and Analysis Solution with Sequential Machine Learning Model using AI and computer vision. So here's a brief overview of our of the presentation. So I'll briefly go over the introduction, goals and challenges, and I'll talk a little bit more in details about our methods, results, and methodology comparisons. And lastly, I'll briefly talk about the conclusion, which includes the limitations and potential future improvements. Okay, so to begin with, we know that caffeine is one of the most consumed substance in modern society, and numerous studies have proven that caffeine consumption in moderation is beneficial to psychological and physiological well-being. However, overconsumption of caffeine can lead to series of health risks, which include high blood pressure, GI tract diseases, headache, cardiovascular diseases such as heart attack. So it is important to keep caffeine usage in check, and this is the motivation for our research. So those are the goals of our research. So first, we wanted to measure the level of caffeine in a cup of coffee by simply taking a picture of it. And we decided to use convolutional neural network, CNN for short, to train a model that recognizes images and returns the level of caffeine. After we finish training a model that's suitable and accurate, we wanted to design an easy-to-use application that returns caffeine level by inputting an image. So those are the challenges we face doing our research. So first is to connect enough data with good quality. So what is considered a good picture of coffee, and how many pictures are enough? Second, we want to make sure our model predict accurately with arbitrary data, because one of the major problems with machine learning models is the overfitting, where the model predicts well within the test data set, but it does not predict well with random data from the internet or from other data set. Third, we want to identify the sweet spot of model training. So because more does not mean better, because like the more we train our model, the higher the epoch is, we might reach the point of diminished return as well as the overfitting problem. So we wanted to see what's the best overall number of epochs we want to have for our model. Lastly, how accurate is accurate enough? So what we consider as a good cutting off point for accuracy that we consider our model is good enough for creating the web application, and what we consider as a success. So here's an overview of our methods. So I basically divided them into three sections. So data selection, data conversion, and training preparation, and the training process itself, and also some other information about the platform we use. So we use Microsoft's Visual Studio Code, and we use Python version 3.10.6, which in my opinion is still the best version. And for web application, we use the combination of HTML and JavaScript, which is also very popular among web designers and programmers. So for data selection, we wanted to select what kind of picture are considered suitable for our data set. So I put an example, a good example and a bad example. So a good example would be a picture of coffee with the majority proportion of the picture as the coffee itself, not the coffee cup, not the background, not the person holding it, which is exactly the bad example is because there are so much space as the background, it will distort the training process. And the bad example will not be a good raw data set for training the model. So as I mentioned previously, we derived our data set from the RoboFlow library. And out of more than 1,000 pictures, we selected 274 images and all in a JPEG format, which are which are more closer to a good example. I put it on the above. So we could not just train the model with the raw images. We have to convert the images into some numerical metrics. So eventually we decided to convert the images into grayscales, just like many other scales describing color. It ranges from 0 to 255. The rationale behind our choice for grayscale was that we care only about how dark the coffee is, not what color it has. And grayscale is basically a scale that measures how black or how white the picture is, specifically how dark the pixel of the picture is. And it's notable that the lower the grayscale, the darker the pixel is. So a grayscale of 0 means pitch black, and a grayscale of 255 means the brightest white you can imagine. So in order to convert the images into grayscale, we used the algorithms from OpenCV. So OpenCV is the largest computer vision library, which they provides numerous ready-to-use image processing algorithms. So by converting our images, the algorithm returns a 2D array of images and its corresponding average grayscale. So basically, we take the mean value of the grayscale of each pixel in the image, and basically we had made a 2D array consisted of these two parameters. Um, since the grayscale ranges from 0 to 255, it's a little bit more too complicated, and also it seems like it's kind of counterintuitive that the darker the coffee is, the lower the grayscale is. So we wanted to make it easier to understand for people who are not in computer science or in art. So we made a benchmark which is a scale from 0 to 10, and 10 is the darkest coffee or the lowest in grayscale, and vice versa. So anything above 195 in grayscale, we consider it as 0, and anything below 75 is 10, and the scale is evenly incremented. So for the training process, first we selected CNN as our neural network. So it stands for convolutional neural network. It's a feed-forward neural network, meaning that it goes in a linear fashion where each layer is only connected to the previous layer and the upcoming layer. So it is good for image recognition and classification, and it contains an input layer, multiple hidden layers, and an output layer. In order to create a CNN, we use TensorFlow's sequential model. It is a model that's designed to make CNN, since a sequential model also has only one input and one output tensor, and the model is also linear. But you can add any number of layers, the hidden layers, as you like. So it's quite flexible and quite simple to use. After we create the model, it was basically just an empty shell. We wanted to use the model.fit function to actually train the model with our data set. So we used the classic train test split with 80-20 ratio, and we use the fit function to train the model. The most important parameter in the fit function is the epochs basically how many times we want to repeat the training, we want to go over the data set. After some testing, we found that epochs of 100 is the best overall in terms of accuracy and efficiency, because anything lower than that would result into a bad accuracy for the model, and anything beyond that would result in diminished return and possibly overfitting. So that's why we decided epochs of 100 the best choice. And any other parameters, after some testing, we decided to just use the default setting, because if we play around with the parameters, it would not benefit the accuracy, if not hurting the accuracy. So here's once we know we're familiar with our methods, here's the structure of our research, where the purple section is the part where we connect and organize our images as the raw data set. And the blue part was the core part of our research, where we create a data set by cleaning them using our criteria for good example and bad example. And then we can create a CNN using TensorFlow's sequential model. And the green section is where we have different prototypes of our coffee prediction models, where we test each one of them. And the one with the best overall results in terms of accuracy and efficiency will be used to create our web application. Okay, so now it's time to talk about our results. So we use some fundamental basic statistical measurements, which are mean absolute error, mean square error, some scatter plot, and residuals, which I'll talk about in detail in following slides. So mean absolute error, MAE, and mean squared error, MSE, they're basically two sides of the same coin, where it measures the average difference between the prediction value and the true value. So as you can see, as the epochs approach 100, the mean error drops to the lowest possible lower value, and the trend becomes flatter. So basically means that anything after 100, we just made the diminished return, where more epochs will result very minimum improvement in accuracy. And the mean absolute error of 6.21 is considered very good, because our grayscale ranges from 0 to 255, and usually the number came out as between 100 to 200. So error of 6.21 is pretty good. And mean square error is basically the same thing, but instead of the average error, we take the average of the square of the error, and so the trend looks pretty similar to each other, and we can say that our prediction was pretty close to the true value. And so for mean errors is basically the average errors of the total predictions, and residuals tells us the errors of individual predictions, as you can see in the graph. So most of our prediction are pretty close to the true value, and it went in a linear fashion, whereas actual intensity and predicted intensity are pretty much close to a 1-to-1 ratio. So we have a R-score of 0.948, where the R-score of 1 means 100% accuracy. So it means that our accuracy is pretty good. And as you can see from the picture on the right, the deviation of our prediction to the actual value was pretty evenly spread out, meaning that our results were not only close to the true value, they're pretty consistent, because the deviation is evenly spread out. It's not skewed to one side or other. Besides of errors, we want to see the effect of background noises on our model. So we divided our images into three categories: the bright lighting, the dim lighting, and the natural lighting. So uh, predictions on images of bright lighting showed the highest accuracy with an average accuracy of 92%. And the dim lighting condition showed the worst accuracy, which was 75%. And the natural showed had a accuracy of 85%. So we can say that the lighting plays pretty significant factors on the accuracy um, of our prediction. So I'd say this is one of the limitation of our research and one possible improvement we can make in the future. But overall, from the statistical measurement of mean MAE and MSE, as well as residuals, we can say that our results are both accurate or valid and precise or consistent. So once we have our model, we made a web application. Just it's a very simple. It was a very simple one, just like the picture showed on the right. It has a submission window where you can input any picture, any format of picture of coffee, and it will return predicted intensity from 0 to 10. And we use both HTML and JavaScript. As you can see, the picture on the left, it's a screenshot of the HTML. And it's worth to note that we only set up our benchmark in the web application. So we did not use the benchmark system in the model training because we wanted to keep the metrics consistent as the grayscale in our training process, and only convert the grayscales into the benchmark in the web application for sake of simplicity and organization. And there are a lot of future optimization that are possible for our web application, since the current version is basically just upload and return value. We wanted to, for example, we can have a saving function where the user can save their past record and to use that record to track their caffeine usage and so on and so forth. All right, so that pretty much concludes the study and the paper. So now I'd like to go over some methodology comparisons with papers done by others in similar topics or they used similar methods. So the first paper I want to talk about was written by Tandon et al. From Sage University in India. So they also use sequential model to make a CNN that detects whether an image of breast tissue is cancerous or not. So they reached an accuracy of 99.61, which is very impressive, but they only tested their data on the test data set, so they could also risk the problem of overfitting. So maybe their accuracy would not be that high with arbitrary data set. Beside the task they perform in their research was basically a yes or no classification. And in contrast, our caffeine detection was more of a classification of different scales, which was slightly more complicated. But since the method they use and the topics they selected were pretty similar to ours, I would say is a good comparison to our paper, and it also shows that you can do a lot of tasks in biology and in medicine with the combination of sequential model and CNN. All right, and the second paper I'm going to talk about was done by Soronis and colleagues from Greece. So they combine an algorithm called SIFT with CNN. So SIFT stands for Scale Invariant Feature Transform. So instead of recognize individual pixels in an image like CNN, SIFT can detect features of an image. For example, as you can see in the picture on the right, they use SIFT to detect lips, human lips, not just lips, but like how the lip looks like. So they can use that as speech recognition. So overall, SIFT is a very popular choice for image recognition. And Soronis and colleagues, they combine SIFT and CNN to make this model called SIFT CNN, where they use this one single model to recognize different categories of images, and they still achieved a fairly high accuracy. As you can see, they not only uh, predict human lips, they predict types of clouds, they predict cell line, and many more. Due to the complexity of their task, they reached they reached an average accuracy of around 80%, which was very impressive. And from their studies, uh, we can use SIFT for further caffeine research. Since the SIFT algorithm can recognize features, so maybe we can use SIFT to recognize only the portion of coffee instead of and they can we can use SIFT to filter out any background noises in our image recognition and training. And the last study I want to talk about was done by Guo and colleagues from China. So they combine CNN and RNN to classify images. So RNN stands for recurrent neural network. As the name suggests, it works with multiple layers and timestamps, and it contains loops. So it works slightly different from CNN, which is a feed-forward or linear neural network. So RNN is traditionally considered good for speech and text recognition. So their combination of CNN and RNN model could recognize images from the rough category to the finer category, which means that they can not only recognize the picture as a bird, they can recognize it as a hummingbird, or they not only recognize the picture as a dog, but a bull terrier, and even better, a Staffordshire Bull Terrier. So beside of this complexity of their task, they also showed a very great accuracy, as their average accuracy was around as above 85%. So from their studies, we can also use the combination of RNN and CNN to not only test uh, the level of caffeine of our coffee, but as well as the type of coffee, for example, Americano, cappuccino, or espresso. So that's all for the comparison part, and I'll talk about the conclusion and the future improvements. So in conclusion, our model can predict caffeine level very well with the input of an image, and the accuracy might not be suitable for lab use, but it is pretty practical tool for daily use. The biggest strength of our model is it's compact, simple, and easy to use. And our results contributes to the application of AI on biology and food science, as well as computer vision. And with our success in caffeine detection, our model can be modified to measure other food or drink. For example, by taking a picture of a soup, we can tell how spicy it is, or by taking a picture of a piece of steak, we can tell how well it is cooked. Um, and for last, I'll talk about some potential future improvements, which I already talked some from the previous comparison section, but now there are a few more. So first, we want to have a better metrics, because we use for our paper, we used a benchmark which was converted from the grayscale. But if we want to better our research, we can use the actual caffeine concentration, like a milligram per milliliter or milligram per liter, which will be a better measurement for caffeine level. However, this will take more resources and more time. So the model can then predict the concentration in actual caffeine concentration with an image of coffee. And speaking of better resource and better time, more time, we can also improve our study with control dataset. So instead of downloading a dataset from RoboFlow, we can take our own picture of coffee. By doing so, we can keep the image uniform in size and proportion. So all images gonna look exactly like the good example I showed before. And we can also take pictures in different lighting for a better noise adaptation for our model. Lastly, uh, beside of our above our beyond our web application, it will be better for daily use to design a mobile app because it is way easier to measure the level of caffeine on your phone than on your computer. So an app on Android or Apple platform will be very good to have. And we can connect the camera with the application where the user can measure the caffeine level by taking a picture, or they can measure the level of caffeine by scanning the coffee directly, and it will return the level of caffeine concentration. And yes, and that's it for my presentation, our paper and research. And thank you for listening.